understand which way it's going to go, I want you to graph me these. Okay, now I'm shifting them. Same exact rules for shifting the graph. Where's this baby going to go? It's going to go down 8. And if you replace x with a quantity, yes, it's going to go left 3. Okay, so when you plot, Jake, we don't want to know. Why is it left 3? If it's x plus 3, you always go opposite sign. Okay, now, since this is an exponential function, when you draw that little coordinate system, what always goes through the coordinate system on an exponential function? What part of the graph do we have to put on right now? The asymptote. The asymptote goes down. That's the new x-axis. So when you shifted it, that's the asymptote. Wherever you find that coordinate system. So your graph will not ever touch that asymptote. All right? Is this one going to be growth or decay? Growth. Because anytime you change... I wrote down. Just like you didn't have the plus 3 anytime you... Yes. So now, you've already dealt with the 3 and the 8. They're taken care of. We've shifted. All you have to do to get points to plot is you're just graphing 4 to the x. You just have to figure out points for 4 to the x.
Why did you change? It was a negative 8 then?
That's a minus 8. X plus 3 power, and then a minus 8 behind it.
Yeah, this isn't going to work out.
What now?
Shouldn't your under down, shouldn't that be a negative 8? No, but you're going down.
Minus 8 means you're going to go down 8. I counted down 8 boxes.
Oh, yeah, that's true.
It sounds like you're negative sign.
Yeah. Remember, when it changes the quantity on x, you go opposite. When it's the number back behind, you go the same direction as the sign. So, in this case, when your base is a 4, you're not going to be able to count to do very many points at all. So, you're going to try maybe 0, 1, 2, 3 if you're lucky. How are you going to get your y coordinates? 4 to the 0, 4 to the first, 4 to the second, 4 to the third.
Why'd you say 0, 1, 2, 3 if you're lucky? 1.
Watch what's going to happen. 1, 4 to the first is 4, 4 to the second is 16, 4 cubed 64. You really want to plot 64 boxes? No. You're only gonna be able to plot up to a 3 with a base of 2. Anything else is gonna go off to your graph paper. So no, you can't freeze. Okay, I dropped this low enough so we could get 16 on there. Yeah. So I could go 0, 1. From this origin, you're going 1 over and 4 up, and then 2 over and 16 up. So no, the negative ones, you're just going to follow the asymptote. So no, you don't have to plot those. You don't need to do negatives. So I know this was 8 to there, and then if I go another 8, 2, 4, 6, 8, that would be 16.
Yeah, that's pretty much straight up.
Yeah, so this baby's going to follow its asymptote and then just shoot up really fast. And that's only with a base of 4. Even a base of 10, you're skyrocketing. I mean, on a base of 10, you're 2 over and 100 up. So, things that grow exponentially are a big deal. All right. This other graph here, we got many other things to learn besides this graphing here. So I'm setting you up for a trick here by writing that as a negative x plus 2 power. Can I tell which way it's going if my x is negative? You have to pull the negative out. You have to factor out a negative, which would make it become x minus 2. So it's actually going right 2. You can't have a negative on x when you're deciding where it shifts. So this one, would it go up or down any? No, because there's no number added in the back. So we would just go right 2, have a new origin, and we would immediately run an asymptote. Okay, how are you going to get your t-table of points on this one? I'm going to go 0, 1, 2, because 3 is going to be too big. And I'm doing what base number? 3. So I'm doing 3 to the 0, 3 to the first, 3 to the second, which is going to give me 1, 3, and 9 to plot. Okay, now, which way does this curve go if there's a negative on the x? Negative on the x makes it, okay, so this baby's coming downward. So when I do my 0, 1, okay, that's straight up from my origin. But when I go 1 over 3 up, I've got to go left, because this thing has to be falling. And then 4, 5, 6, 7, 8, 9. I'm going to be falling some more. It's going to come downward, not upward, or not to the right, anyhow. And we got exponential decay going. All right. Now that you're graphing experts, let's go put these babies to some use.
How many fans do you have?
How many what?
How many fans do you have?
Yeah. We're going to solve some exponential equations. This that I'm about to teach you is going to be the bottom step of logarithm problems. So I suggest you tune in. That we will learn on Thursday. What's a logarithm?
It sounds like something that requires a lot of work.
No, it's actually not any more work than any of the other problems you solve.
Really, like rhythm.
All right. I actually want you to solve for x. I want you to figure out what number you put it in for x would make these two things equal. All right? So you're trying to guess what could I put in for x, and then take 11 to whatever that power is, and those two sides would equal each other. There is a method or a strategy for doing this. What you need to do is you need to make the two base numbers become the same number by rewriting one or both of them to a smaller base. So, what's in common? What do you know about 11 and 121? 121 is 11 squared. So if I rewrote that as 11 squared, I would make them both have the same base. Okay, so I'm going to leave this side alone. It's happy. Now, I changed this to 11 squared, but 3 minus x would still be on the outside. Okay, exponent rules, here they come. Add or multiply. I would multiply, so that would become 11 to the 6 minus 2x. Okay, once you get both sides all simplified and have the same base, they're both 11. If the bases are equal, wouldn't the exponents then have to be equal too? So once you get the bases to be the same, you can drop the bases and you just go with the exponents. And you say, well then 2x plus 3 has to equal 6 minus 2x. And you can do normal solve for x. So yeah, add 2x over would be 4x, subtract 3, we'd get 3, and x would equal, and that's all you have to do. You have to get them, the key thing, the trick is getting them changed into the same base. And it's going to make you use your rules of exponents that we just studied. So that one.
Other ones more confusing?
Well, with a touch more challenge to them, yeah. The key thing is make them have common bases. So, you're saying you need a little more challenge.
No. When did we ever say that?
I know you said that. I have telepathy. I can read your minds. I can go. That was too easy. She's insulting our intelligence.
Tell me, what am I thinking?
How many minutes are left in this file?
Probably pretty much.
Okay, so you look at one of these problems and you go, what would be common to a 9 and a 27? You want to rewrite them. If you change them, you must rewrite them as a smaller base number. You cannot make it get a bigger base number. So what do you know about 9 and 27? They are both powers of 3, aren't they?
Oh, yeah.
Can't they both be written as 3 to some power? Yeah. So 9 could be changed into 1 over 3 squared. And 27 could be changed into So 3 to the what? 3 to the third is 27, yes. Okay. So now, you have to get them both up top, written as 3 to a power. How do I bring this dude up?
You could make the exponent negative.
Yeah, I'd bring the exponent up, make it a negative 2. It's got a 4x on the outside. What's that really going to become? Eric, this is important. To him. No, you aren't. You're talking to him and looking that way. That's negative 8x. Okay, what can I do to the right-hand side? Uh-huh. Okay, so now, do you have them both with the same base? So if the bases are equal, then you can set the exponents equal. And say negative 8x must equal 3x plus 6. Which would give me 11x. Bring the 6 over. And so I would get a negative 6/11. So is that horrible? Okay, the key thing, yeah, it's a lot of steps. The key thing is most people struggle with finding the common base number. And I'm not going to use horrible strange weird numbers. 9 and 27, they can both be written as 3 to a power. 27 is 3 to a power. You have to find a smaller base number that they can be written as. Can I roll? Because I'm going to want to do one other quick one. How am I doing? Yeah, okay. I can do one more. And this one I'm more worried that you remember your rules of exponents. What if I gave you cube root of 4 to the x power equals 1/8 to the 5 minus x? Okay. What's a common number you can rewrite both of them as something to a power? I got a 2 squared and 2 cubed. What do y'all think? Because I can't write 8, there's 4 to a power doesn't work. 8 isn't 4 to a power. So I have to take them both back to 2. So I'm going to change this one to 2 squared, so that's going to just make me have 2x. What's this one going to become? 2 to the what power? Third. Maybe, do I need to do that in 2 steps? Can I bring it up? It's going to be 2 to the negative 3 because I have to bring it up. Okay, that's what I was afraid of. 1 over 2 cubed. 8's 2 cubed. Do I have any more room? Definitely not. Okay. So then, when I bring it up, it becomes 2 to the negative 3. And I got the 5 minus x on the outside. Okay. How am I going to rewrite this root as a power? I need a 2 to a power. How do you write a root as a power? You're in big trouble if you don't remember this. Fraction, thank you. Yes, that's 2x over 3. That's just a fraction. So I told you those exponent rules were going to haunt us. So, okay, if that side's 2 to the 2x over 3, what do I need to do to the right-hand side since I need to multiply those, yeah. So that would make me have negative 15 plus 3x. So now are you down to a single base, same number, and I'm coming over here to the left where I got room. So then I can set the exponents equal. How are you going to solve for x when you got fraction action? Yeah.
Well, we gotta multiply by 3.
I would times it all by 3, which will leave me with 2x. Negative 45 plus 9x, yeah, kind of a big number. So then if I subtract the 2x and add the 45, I'm going to end up with a lovely 45/7. I'm sure that's what you guessed the answer to be. Obviously, yes. Okay. That's an important skill if they come back to hunt. You're going to use the next class to solve log problems.
It always comes back to hunt.
It does always come back. Math builds on itself and it gets you when you're least looking. I do. It's fascinating that it keeps recreating itself. It's awesome. Okay, stopping.